Hey everyone, welcome to the last part of 2.3. This is higher order differentials and actually a word problem. The proof for the power product, that's not right. Let me see if I can get this right. The proof of the power rule is actually on page 118 if you want to see it. I'm not actually going to go through it, but it is there for you to check out if you so desire. Alright, now let's talk about higher order derivatives. You can find the velocity function or the velocity by taking the derivative of a position function, right? So when we had like s of t with the diver and all that kind of stuff, you figured out how fast they were going when they hit the water, right? But what happens if you have a derivative of the velocity function? What is that called? I'm going to tell you later on, but right now we're going to say that this is called the second derivative. You can actually take a derivative of a derivative. That's right, a derivative of a derivative. Okay, so it's kind of like math inception. Ooh. Alright, so now what we're going to do is just see some notation for the second derivatives, third derivatives, and so on. So let's say we have our original function is y. First derivative you know is y prime. Second derivative, y double prime. Third derivative, y triple prime. There we go. And if we say it's an nth derivative, we can keep on going for a long time. We can say this is y to the nth. Watch this. Ha! It's like I'm writing in two places at once. Okay, so if it's a function, f of x, we'd say f prime of x. See? Ha! The second derivative is f double prime of x. Here's my marker still writing. Look at that. Third derivative, f triple prime of x. And then we just say that's f to the nth of x. This doesn't come up very often, but just as a hint. Okay, we also have d dx is actually the first derivative. The second derivative would be d squared over dx squared. And then the third derivative is d cubed over dx cubed. And then that would be d to the n over dx to the n. Alright, dy dx. This one looks kind of weird because it's not exactly the same. It's going to be, the first derivative is dy dx. Second derivative is d squared y over dx squared. The squared goes later. And the same thing, d3, d cubed y dx squared. And then that keeps going to dny over dx squared. And the last one, if you see something like this one, dx, and then the square brackets y, is going to be something like, that's really the first derivative. Again, I didn't have a good shorthand for the original function. That's going to be dx squared bracket y. And then it's dx cubed square bracket y. And then we keep going dx to the n square bracket y. Okay, oh, you can't quite see it. And there you can now. Okay, so there you go. That's just examples of some notation. So we can take the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, 100th derivative. We can keep on going forever with derivatives, but that's not going to be really what happens. Usually it's first, second, third are kind of the most important, especially when you get in like Calc 2, Calc 3. Will become a little bit more important. So let's do this one more example. Acceleration due to gravity. The moon has no atmosphere, so there's no air resistance. Actually, someone did this. They had a hammer and a feather. They dropped them, and they fell at the exact same rate because there wasn't air to slow it down. So the position function on the moon for a falling object is s of t equals negative 0.81 t squared plus 2, where s is height in meters and t is time in seconds. So they dropped it from something where about 2 meters. Okay. We want to know is what is the ratio of the Earth's gravity force to the moon's. So we know the Earth's gravity force in meters is going to be negative 9.8 meters per second squared. Right, so now you might have always thought, like, why is it meters per second squared? Why does that really matter? Because really what we're doing is we're taking, we've got meters, we're dividing by seconds, and we're dividing by seconds again for that second order derivative. So that's on the Earth. E-A-R-T-H, Earth. Okay, so now let's use this function to find the first order. What's the velocity on the moon? So the velocity is going to be s prime of t equals, and we're going to take that 2, put it in front, so it's going to be 2 times 0.81 t. That 2 is going to cancel out, right? Good. Okay, and if we want to find the s double prime of t, to find that second order derivative, the word that I was looking for you to say before was called acceleration. That is, acceleration is the second order, or the derivative of the velocity function. So we're trying to find the acceleration due to gravity. So it's s double prime of t, which is really just going to be 2 times 0.81. 2 times 0.81 is going to be 1.62. So our double prime, the acceleration due to gravity, is 1.62 on the moon. So then we want to say, what is the ratio of the Earth's gravity to the moon's? We're going to say, oh, and that should be a negative right there, because this was a negative here. I did make a mistake because it's still there. Yep, good. Okay, so the Earth's gravity, E-A-R-T-H over moon. So that's what we're going to write. Make sure we have them in the right spots. It's going to be negative 9.8 over negative 1.62. So if we clean that up, what's the ratio of those two things? It's about equal to 6.05, which means the Earth's gravity is about 6 times stronger than the moon's. So if you want to learn to jump really high, jump on the Earth for a long time, then go to the moon, you're going to be able to jump 6 times higher than you normally would. Alright, there you go. There's the rest of this section. Good luck on your assignment.